Synchronization is about putting stuff in order, consistency is about putting stuff in order. Okay. So, with sequential consistency, there's basically two things in sequential consistency that we have to observe, okay? The operations themselves have got to be in some sequential order, right? And each one of those processes have got to be in the order that's specified by this program, right? So it means we can interweave these operations pretty much any way that we want to, provided we see them in the same place everywhere that they're observed. Okay. So again, kind of reviewing this shorthand notation here. We got P1, P2. These things are processes that are running across the network. X is the variable that they're going to be working on. Okay. W is going to be a writing operation. R is going to be a read operation. So you're writing to X, and you're reading from X. Okay. So what we have right here, P1 is going to write the value A to X. Sometime later on, P2 is going to actually read that value, observe that value, okay? And when it attempts to observe that value, it doesn't get anything out of it. So when we see that, what's going on? What's being depicted?
P2's clock is
Sorry?
P2's clock is before P1's clock.
Okay, say that for me again.
P2's clock is before P1's clock.
Not necessarily. That's possible, but that's not what's happening here. Right? The clocks are never going to be synchronized, so we know that. But that's not what's happening here. So these two things are attached across a network, right? Does anything travel instantly across a network? No. Do things arrive in order that you sent them on a network? No. Sometimes things disappear, they are never seen again. Okay. So what's happening here, what's being depicted in this particular diagram, okay, you're writing that A to that X, okay, and it takes time to propagate over here at P2. Okay, so when P2 goes to actually read X and see if there's anything in there, initially it doesn't get anything. Some other time, okay, a little bit of time later, it reads an X and actually sees that A. That's just network propagation. Okay, so stuff slows down, stuff's delivered out of order, stuff gets lost, all kinds of funky things happen. Okay, so ultimately what this is about is just making sure that we observe things in order. Okay, so up here in A, we have something that is sequentially consistent. Down here in B, sequentially inconsistent. So P1, P2, P4, P3, P4, these things are connected across a network. P1, first thing that happens, writes an A to X. Okay. P2, later on, writes a B to X. Okay. When they first read this value, there's a couple of different things you might expect to happen. Well, you could say, well, okay, maybe that B overwrote that A. Right, so P3 and P4 should see that B first. Or you could say, well, it wrote that A first, and since that's the first thing that happened, they should observe that A first. Either one of those things could be the case, right? But because we can't predict how things are going to propagate through a network, they can be delivered out of order, delivered with latency and all that kind of stuff, we're never really sure what processes are going to see. So we're not trying to dictate that, we just want to make sure that everybody sees things in the same order, regardless of what that order is. Okay, so the first thing P3 and P4 see is that B, and that's fine. And then later on when they go to read that value, they see that A, and that's fine. Because P3 and P4 saw the same thing in the same order. That's okay. Okay, down here, what is happening is, again, it doesn't matter if they see that B first or if they see that A first, but they have to see the same thing. Because if they read those values in different orders, then what we're going to end up on the other side is something that is inconsistent. Okay, now again, ultimately, what is consistency? We're just talking about consistency in general terms. What is that? Consistency is just agreement, and that's all it is. Okay, so you say, well, what exactly is agreement? And agreement is whatever we agree agreement is. And I know that sounds kind of like a cop-out, but it's true. All right, so if we say, hey, if it looks like this, that's fine. Well, okay, as long as everybody agrees that that's what that looks like is consistent, you're good to go. Okay, so that's sequentially consistent. That's the same thing in the same order. The other part about sequential consistency is that you got to see things in the order that's specified by its program. Okay, so what we have here, we have different interleavings between these processes. Okay, so process P1 is going to write a 1 to X, it's going to print YZ. Process P2 is writing a 1 to Y, going to print XZ. Process P3 is going to write a 1 to Z, going to print an XY. one of these interleavings is valid, fine. So we got, let's look at D. Okay, so we got a one being written to X, that's the first operation from P1. Got a one being written to Y, first operation from P2. Print XZ, that's the second operation from P2. Print YZ, second operation from P1. We have P3. That's fine. As long as everybody in the network sees that same thing, it's no problem. When would this not be correct? What would we have to observe in here that would break this? Okay. Let's say we had one being assigned Z. That's sequentially consistent with what we have up here. Yes, no, maybe, sort of, what's wrong with it?
The Y should be before the print XC.
Okay, so what's happening here? Z1, okay, that's the first operation from process P3. That's from process P3. Print XY, that's the second operation from process P3. Those two things are in the order specified by the program, good to go, no issue there. Okay, what do we see with this next one? We got a print XZ, where's that from?
P2.
Process P2, okay, is that the first or the second operation from process P2? It's the second operation. First operation is actually gonna be that one. Okay, that's not okay. All right, these two things would need to be in reverse order. You would have to switch those around. So it doesn't matter how these things get interwoven. As long as everybody sees the same thing, nobody cares. But they still have to execute in the order that's specified by the program. And if you get them out of order, then you've broken sequential consistency. Does that make sense, what we're looking at here? Okay, and don't pay any attention to this print signature. I've been looking at this stuff for years, I still have no idea what that means. Okay. Okay, so that's sequential consistency. Something else I want to cover is causal consistency. Okay, when we say causal, two things are causally related. What does that mean? We talked about that with vector clocks. Two things are causally related. One may have caused the other. Okay, may have. It's possible. That's not guarantee that it did. It's just possible. If we wanted to guarantee that one event caused another, what would we have to do? We have to start looking at semantics, right? And we don't really like semantics. That's hard for us to do programmatically. Okay, so that's why we have to say, well, maybe it caused it, possible it didn't, maybe it did. Okay. So what we have to do is that if two events are causally related, then we have to see them in the order that they happen. If they are not causally related, then we don't care the order we observe them in, because they couldn't have had an impact on one another. Okay. So what does that mean? We kind of look at this, okay, same kind of nomenclature, right? You got the WXA, all that kind of stuff. P1, P2, P3, P4. Here's the thing. WXA is the first thing that P1 does. And then everybody in that particular system observes A. Sometime afterwards, P2 writes that B. Okay? So what we are looking at from a syntactical programmatic standpoint is we say, okay, P2 saw that write. It saw that write with that particular read. It is possible that because it observed that particular read, that value being coming, or see that value coming out of X, that when it read that value, it resulted in that write. It's possible. Could have been some kind of if statement that says, hey, if that equals A, then we're going to go ahead and write this. That's what we're saying. So if we observe it, if we see it, it's possible it could have changed our behavior. And because it's possible it could have changed our behavior, it's causally related. You guys see what we're saying? If we do not observe a write, then there's no way it could have changed our behavior. Right? It's kind of like with vector clocks. Just because we're omniscient, we can see that there's a lot of work being done. But if if those processes don't actually receive that message, it doesn't matter. Okay, so XA and, WXA and WXB are causally related. And because they're causally related, they have to be seen in the order that they happen. WXB, WXC, does P1 ever see that right? No, it doesn't. Okay, because it does not see that right, these two things cannot possibly be related to one another. Okay, because P1 never saw that value B, there is no way that that right could have changed P1's behavior. And if it could not have changed its behavior, it's not causally related, we can see it whatever order we want. Okay, so what happens is, WXB, WXC, they are not causally related, they had nothing to do with one another. And because they could not have impacted one another, it does not matter how they are observed in the network. They can be observed in any order anywhere, no big deal. Okay, this is a violation of causal consistency. Once again, P2 sees that right. Okay, and because it observed that right, it's possible that observing that right changed its behavior. So WXA and WXB are causally related. Okay, if they are causally related, they have to be seen in the order that they happen. And down here, they are not. Okay, if we wanted to break that causal relationship, what would we do? We'd have to remove that read. Okay, so now, is there any way that that value A could have changed P2's behaviors? No, because P2 never saw it, never read it. And if you never read something, if you were not aware that something happened, there's no way it could have changed your behavior. It's not magic, right? So because it couldn't have changed your behavior, they are no longer causally related, doesn't matter the order you see it in. Okay. So are you guys clear with what's happening here, what we're looking at, and everything else? All right, let's do a second example. We got a few minutes. Okay, now, WXA at P1 and WXB at P3, are those two things causally related? Causally related, excuse me. No, they're not. How would we make them causally related? You'd have to add a read right here, you'd have to observe that read. Okay. Now, it's also possible, more than one thing can be causally related to something else. Okay, I mean, you can have a conditional, you can have if statements that have multiple conditions to them. So you have to see this, you have to see this, you have to see this. Okay, so it's possible that more than one event could be causally related to something else. So if we wanted to add another read here, say read XC, and then we have, okay, is WXB causally related to WXC? Yeah, we saw it, and if we saw it, it could have changed our behavior. If it changed our behavior, it's causally related. Okay, so it's possible that more than one thing are causally related to something. Okay, are we clear on why that is? We gotta see it for us to affect us. Yes, question?
On causal consistency, slide 3, this is a violation because of the order P3 and P4 read?
Yes. So what's happening here, because this read, or excuse me, that right could have affected that right, we would both need to see that A first, then that B. So that's why it's causally, it breaks that causally.
We have to see them in the order, both see A first and then they both see B?
Yes, they would both have to see A first.
And then, so, in the slide after that, causal consistency, slide 2. So, is there a violation here too?
No, okay, because we're not seeing A. If they saw A, then at that point, they would have to see B in the same order. Now the one was actually.
Okay, so it has,
If you're not actually observing that value, you can't change it. Okay. Alright, are you clear on what's going on here? Okay. So, this is a way that we can do all of this concurrently. One other thing that we can do is what is called grouping operations. Okay, Roofing operations just means that we have locks. Okay. So, this is just a slightly different way of doing this. Here, what we're doing basically is we're defining what are called critical sections. Okay, so, this is another way of enforcing mutual exclusion. Right, so with synchronization, we had a way of enforcing mutual exclusion at the device level. We would only let one device do something. Okay, here what we're doing is we're enforcing mutual exclusion at the variable level. Okay, now, a whole bunch of text here that kind of describes something that is relatively basic. Okay, so again, don't worry about the gibberish of the textbook. Here's what we're looking at. L is a lock. When you have that lock, it means you are the only one who can actually read or write to that particular variable. Okay. ACQ means you acquire that lock. REL means you have to release that lock. Okay. So what is going on here? P1 needs to write to X, so it acquires the lock to X. Once it has that lock, it can write to that variable. Okay. Later on, it decides it needs to write to Y. So it acquires the lock to Y, writes to that particular variable. Then once it's done, it releases both of those locks. Okay. Now, you have what is called an exclusive access, which means if you have that lock, you cannot even read what is in the other variable. Or excuse me, somebody else can't even read what's in it. So P2 later acquires that lock, reads A from X. It attempts to read Y, doesn't get anything out of there. What's happening there? Sorry?
P3 got the law.
P3 got the lock. Okay. So if you have a situation where P2 is waiting on P3, okay, P3 is waiting on P2, right, they both have assets that both of them are waiting for, they're both locked, what do you call that?
Deadlock.
It's a deadlock. Because everybody's waiting on everybody else to do something. Okay. Again, don't worry too much about that wall of text. That wall of text is just saying what's going on. Okay, so concurrent consistency, mutual exclusive consistency, do we see what's going on? Okay, that is the last part on chapter 7 that I'm gonna cover for the 10. Okay, there might be another little piece of it after the test, okay? Then we'll cover fault tolerance, we'll get into the mobile system stuff. Okay, so, this is going to be when we have the opportunity to review whatever it is you guys wanna review. Okay, so if you guys have questions, whatever, right? This is your opportunity to ask about it. So, questions? Yes,
How long is it?
how long is the test? I haven't read it yet, I don't know. Okay, probably gonna be 20-ish questions, okay? Not gonna be super long. Other questions? Questions regarding the material? Yes,
Could you maybe do another example of like the distributed hash tables again?
hash table, okay.
Yeah.
So. We'll just leave that blank for now, because the math gets a little tricky. Okay, so. What determines our size of hash tables in, when we're using hash tables? What decides the size of our finger table when we're using DHTs? It's the number of bits in our address space. Okay. So if we want to support 16 addresses, how large is our finger table gonna be? 4. 2 to the 4th, right? So 2 to the 4th, we would support 16 addresses. So again, all of this kind of goes back to, right, hash tables. Okay, so we want to support however many addresses. Some of those addresses may not be huge, we may not have active systems, but if we want to support that, okay, how many do we have to have? Right. Now, let's say okay, so how many nodes do we have? We got to do that correctly. Okay. get nodes, how large our address space? Okay. Right, so to the third, so each one of those finger tables is gonna have 3 entries on it. Now, there's different types of distributed hash tables out there, and we're focusing on chord. Okay, they all work very similar to one another, but if you look up YouTube or whatever, just make sure you look at chord, because they all work just a little bit different. In chord, how do we move around that overlay network? How are we going around that circle? We always go clockwise. Okay, we never work backwards, not in chord we don't. Okay. So, when we're doing this, we gotta set up our tables. Okay, again, the math on this, it looks a lot more sophisticated than it actually is. Okay, so, let's just go around here, fill this out, okay? And if we need to review the math, we'll review the math. What is going to be the finger table for 0? Okay. It's gonna be 1, then 2, and 2, and 4. Okay. Okay. Finger table for 1.
2, 3,
Nine. Okay. So, here's what's happening on every one of these things. It does not matter which node you start off, it's always gonna follow the same pattern. First entry in your finger table is always going to be your immediate successor. Second entry in your finger table is always going to be the node that comes after it. Okay. The last entry in your finger table, no matter how large your finger table is always going to take you halfway across the network. At least halfway across the network. And it doesn't matter where you are. Okay? So again, what's gonna be the finger table for 6? It's gonna be 7. Okay, so again, sketching out our pointers here. What's happening? First one, 7. That's how it looks, no matter where you are. Okay? So again, the formula and everything else, you know, the textbook has to make the formula look as sophisticated as possible, because it's a graduate level textbook. Okay? But it's really pretty simple. Okay, so what happens now, if we have some of these addresses that are available, but let's say we don't have nodes that are actually running at that particular address. So it's an address that's available, but a node is not actually there. So let's say that we have 0, we got 0 available, but it's not there. Let's say it's 7, it's not there either. Okay, so we need to redraw this finger table. What's gonna be 6's first entry in that finger table?
1.
It would have been 7, 7's not there. In chord, we always navigate clockwise around the circle. 0's not there, so what we do is we just traverse that circle until we find someone who is there. 0's not there, 7's not there, 0's not there, 1's there. But 1. What's gonna be the second entry? 0's not there, from wherever we are, we traverse the circle until we find somebody that is there. Ends up being 1. Okay, and then what's the last entry? 2 is actually there, ends up being 2. Okay. Let's work on this larger example. Something like that is probably what's gonna end up being on the test, just because I really don't wanna go into PowerPoint and draw this. Okay, so let's kind of look at what's going on here. Building the finger table for 1. Okay. What would be 1's first entry in the finger table?
2.
Would be 2, 2's not there, gotta traverse around until you find someone that is there. 4. What would be the second entry?
3.
Would be 3, 3's not there, gotta traverse around the table until you find something that is there. 3. Okay, so you guys clear with what's going on here? Okay, we got questions on this, why we're doing this? What's the point of distributed hash table? they're frequently used in peer-to-peer networks, but why are they used in peer-to-peer networks? It's decentralized. It's a decentralized database. Okay, and so what distributed hash tables court, specifically the address spacing court, I believe, is defaulted at like 128 bits or something like that. It is a massive, huge address space. But because it's decentralized, there is no one node in the network that has to keep track of every other node. The only nodes you have to keep track of are the nodes that are actually in your finger table. So by having this sort of decentralized network, you can begin a search at whatever node you happen to land on, and eventually, you're going to terminate at the same key no matter where. Now, I'm not gonna ask you guys to do lookups on these things, just because the textbook's example of lookups is terrible as English. Okay, but if you can set up those tables, right, you'll be fine. Okay, other questions?
Just a couple, the lookup is, resolve stuff that we did last time, where it says resolve that, is that what you're referring to when you say lookups?
Yeah,
Okay.
right, so k equals 12, right, what you're gonna do is look for k equal 12 inside of that table. Okay, and then basically what you do is you're trying to traverse around the range as far as you can go without going past the value that you're trying to hit. Okay, again, look, they're actually pretty simple, it's just how the textbook explains them is, I hate how the textbook explains it, so. No, you're not gonna have to do a lookup, so you don't worry about lookups. Okay, I mean, it's not that they're hard, it's just I like how the textbook explains it.
Whenever we were talking about, disconnecting from the network or the server crashes, and we have to go back to the root server, you know, that,
Oh,
is
DNS?
the authoritative level server the same as our local DNS server?
Okay, let's go back and review the list. I did put these slides up online, right?
Yes.
Okay. Just go through, we'll step through DNS real quick. Okay. I think it's in the chat.
Yeah, right there.
Nothing, was that it? No, that's okay. Oh, here we go, okay. So. Have what we call a closure mechanism, right? What's a closure mechanism? Closure mechanism is the first place we begin a search. Okay, so that's the very first step. Our closure mechanism in DNS is what? Where do we always begin a lookup in DNS?
The root server.
No. Your local DNS server. That's where you always begin your lookup. Now, the trick is, when you join a network, you have to be told where your local server is. It tells you where your local server is. It's a good thing we're here. So who tells you where your local server is? How do you get an IP address if you join a network for the first time? Network of people.
DNA?
DHCP. Okay, DHCP is gonna give you your address, DHCP is gonna tell you where your local DNS server is as well. Okay, because it may not be in the same place, it doesn't really fit in a hierarchy. So what you do is, okay, you're gonna begin with, what's called an iterated query or an iterative query, okay? What's gonna happen is, we got this requesting host, poly.edu, okay? So sys.poly.edu is gonna try and find Guy over here at UMass. We are assuming in this example that your local DNS server has just now come back online. Okay, so it's been offline, it lost everything that it had there. So it's clueless, it has no idea where anything is. If you have no idea where anything is, okay, first thing you're gonna do is connect to your local DNS server, say, hey, trying to find this guy over here. Okay, your local DNS server, again, it's clueless, it's never looked up anything. If you have never looked up anything, you go to the root. Okay, and what you are trying to find is the top level domain server for .edu. Root is gonna reply with the top level domain servers, a list of top level domain servers for .edu. When you get that list, what do you do with it? Okay, you keep a copy of it. Okay? You keep a copy of it because you don't wanna have to go to the root every single time. So if anybody on that same network comes along after you that looks up an address on the .edu servers, we don't have to go pester the root. Okay, that's why we keep a copy of it, right? So, what did we just get from the root DNS server? What does the root DNS servers keep track of? The top level domain servers. Okay, let's take a step back. So here's our hierarchy. Okay, we've got our root server. All our root server keeps track of is a list of the top level domain servers. And that's it. It keeps track of nothing else. All our top level domain servers do is keep track of our authoritative servers. And that's it. They track nothing else. All our authoritative servers do is keep track of the addresses on their particular network, and that's it. So what is actually being stored at each one of these levels in the hierarchy is really not that much information, relatively speaking, right? It's not like a copy of the entire internet, that's impossible. Really, all it's doing is just pointing to different databases. So when we go to the root, the only thing the root keeps track of is a list of top-level domain servers. Okay, so we go off to there. Right, what are we looking up at that top level domain server? Yeah, again, the top level domain servers only keep track of those authoritative servers, that's it. So we're trying to figure out what that authoritative server is. It applies there. Now we have an address to the authoritative server. Go off to the authoritative server, what are we looking up at that authoritative server? It's the address of the actual end system that we're trying to get a hold of. That's all the authoritative servers keep track of, the stuff that's on their network. Okay? So that's umass.edu, that's a computer on umass.edu, that's all the authoritative server keeps track of. Returns that. Okay? At each step, when something goes through your local DNS server, you cache it, keep a copy of it. And that's so that either you or anyone else who is on your network does not have to look it up a second time. You got a copy of it. So, go to your authoritative DNS server. Finally, you have an actual address that is returned to you. And when you get that address, that's when you can actually go and connect directly to that particular system. Okay?
What if somebody's trying to find the host? Does that make the DNS server our authoritative server for somebody coming the other direction, trying to find us?
You mean if somebody is coming from outside your network and attempting to find poly.edu or assist.poly.edu?
Well, I mean, yeah, us.
Yeah, and so what's gonna happen is inside of your network,
Mhm.
your authoritative server is gonna keep track of your position. But here's the thing with the host, local DNS server, that really doesn't fit in the hierarchy. And we got a slide about that. Okay, now, it doesn't strictly belong to the hierarchy. Sometimes it could be the same as your authoritative DNS server, could be. Okay. However, you can actually point to whatever DNS server you want. If you want to use Google's DNS server, you can point to Google's DNS server, and that will be treated as your local server. Okay. If you're using a VPN, whatever DNS or whatever DNS server your VPN is using, that's going to be treated as your local server. Okay. So it's possible that they are the same thing, but it's not necessarily the case that they're the same thing. It can be switched. Does that make sense?
It's just like the process can,
That's fine.
the DNS process can be on any server.
Yeah, well, the DNS server is just a program. Yeah, I mean, that's all it is. And so, yeah, you can run your own DNS server at home if you want to. You know, you just set up a file on your program and say, hey, check the file for something we have cached. I wouldn't recommend doing that, but it's possible. But yeah, you can set it up wherever you want. But your authoritative server is going to be what's responsible for keeping track of you while you're on the network. Okay. Right. So, why is DNS not particularly well suited for keeping track of nodes that move around a lot? It doesn't work very well for mobile nodes, right?
Because of all the caching.
Yeah, because of all the caching. Okay, so if this were, you know, a laptop or something, and that laptop's moving around a lot, well, you're gonna get a different IP address probably every time you connect to the network. Alright, because that's what DHCP does. When nobody's using that IP address anymore, releases it, gets rid of it. Okay, so you're gonna get a different IP address. Well, the trouble is, who even knows how many different places that address has been cached? And we cannot not preemptively go off and find each one of the copies that have been made and update all of those copies. That's way, way too expensive. Okay, so DNS is not really good at keeping track of notes that move around a lot. If you're static, it's great, right, it's what the internet uses, but if you're mobile, not so much. Okay. Other questions? You guys are completely good to go. Okay, I'll hang around for a couple minutes, so you guys come up with any more questions, okay? If you got questions over the weekend or whatever, email me and let me know, okay? I'll check my email a couple times over the weekend. Test itself, again, I haven't written it yet, but it's gonna be 20 to 25-ish questions, okay? Nothing big, okay? And then again, lab's gonna be due on Monday as well. Okay, so what you need to do, just upload your code to Blackboard so we have it. EA is gonna call you in to actually demo it, so you can demo it on your own equipment. Right, we're definitely not gonna try and get your Bluetooth code running on our own devices, okay? You guys should understand why we want that. Okay. All right, guys, if you don't have any questions,